Hey everybody. We're going to do an example this time of a uniform distribution. Excuse me. So I've written down what we have already figured out about the uniform distribution. Make this symbol a little better. A uniform distribution, we're talking about a continuous random variable. This is just the symbol we've been using. U for uniform, and the A and the B give the smallest and greatest possible values of this uniform distribution. We know that the mean, or the expected value of a uniform distribution, is the sum of these two endpoints divided by 2, in other words, the average of them. And then we have this little formula for the standard deviation that you can derive using calculus. In any event, let's go ahead and look at this question. So the thing we want to imagine in this question is that we have arrived at a bus stop. We don't know what time it is. We just know that the bus comes every 10 minutes. Okay, so we may have just missed the last bus. The last bus may have gone by a while ago. So we don't really know at all how long we're going to have to wait, other than it could arrive immediately from the moment we get there to 10 minutes later. Okay, so 2 questions I want to start with, and we'll do one more at the end. What's our expected wait time? And then what is the probability that I wait more than 8 minutes? Okay, so we could jump, depending on how much work you've done with uniform distributions, you might be able to just jump to these answers. I want to really take our time to build out to do all the steps, naming a random variable, defining its properties, all those kinds of things. This is a skill that is going to become more and more crucial as we move into more and more complicated problems. And so even if this one fits in your brain well in a way that you don't have to go through all this to get the right answer, it's a good place to practice before we get to the harder stuff. Okay, so I'm going to start by defining a random variable. I'll use W. That's going to be the wait time. Okay. For bus arrival, I guess. Oops. And I should say this will be in minutes. And we're going to assume that W follows a uniform distribution. Since we don't know what time it is, any amount of time from now until the 10 minutes, right? I'm living in a fantasy world where buses are never late. So it's absolutely not going to take longer than 10 minutes, but it could be any moment between now and those 10 minutes. So that means the minimum wait time is 0 and the maximum is 10. Okay, so there's our random variable defined. So I guess I'll put a U on there. Stem. So our expected wait time, right? This is really our expected value, or our average wait time, is what we mean by this. And the right way to think about this, or a good way to think about this, is if I were to show up at this bus stop in the same way day after day after day after day, what would the average wait time tend to be, right? Some days I might show up and it's just arriving. Some days I sit there and wait for almost 10 minutes. Sometimes I wait a little bit less than 4 or 5 minutes. Sometimes I wait a little longer. What would that tend to average towards? And that's this expected value, or mean. So in this case, the mean, maybe I'll put a little index on it for this random variable, is the minimum plus the maximum divided by 2, or 5 minutes, right? Which is what we expect. If it takes anywhere between 0 and 10 with even probability, then right in the middle is what we would tend to expect. That there would be some days it takes 2 minutes, some days it takes 8, some days 3, sometimes 6.5, and on average it tends towards 5 minutes if we kept arriving in this way. Okay, so let's now look at the probability. And for the probability, I want to go ahead and make a graph. All right. Again, this isn't absolutely strictly necessary, but I think it's worthwhile to do, especially in the beginning. So I'm going to give myself a little graph here. Let me change this. Let's make it there, and let's make it black. All right. And here's another one. So here's my axes, and along and along the horizontal axis is going to be the wait times. Right, and the way we do these is just 10. Sorry, I was having trouble remembering what the problem was, even though it's right in front of me. So I'm just marking off 10 just to give myself a little bit of a scale there, and I know I need to go to 10. The way we represent this uniform continuous distribution, all times being equally likely, remember with our probability distribution functions or our density graphs, the meaning of them is a little tricky to get behind, to get around. We're not going to dive deep into that, but I think a good way for us to think about them is they represent the relative probability of each moment. And so if I do a probability density function, the places where it's highest are the most likely places for things to happen, times or locations or whatever the case may be, and the places that are lowest are the least likely. Since all times are equally likely in this case, we get a horizontal line. There's no time that's more likely than any other time. Let's change this red, make it a little thinner. And so that's our distribution function. There we go. That's our distribution function. This simple, oh, why did it change to, I wanted it to be red. All right, let's stay there. Okay. All right, sorry about that. So there's our distribution function. And one thing we need is how high it is. And remember, the way we get that is we realize that the area of this whole thing, right? So let me remind us this connection. Probabilities for these continuous distributions or continuous random variables are related to area. And in this case, the area between 0 to 10 is all, that's our sample space. It's all possible outcomes. And so that area has to equal 1. And the area is just a rectangle. I know the width is 10. So in order for the area to be 1, the height has to be 1/10, right? Remember, this is 1 over b minus a. B minus a just represents the width, and then the height is the inverse of that. If you want to think about it, what that means is the units of our vertical axis are 1 over minutes or per minute. And it's kind of like likelihood per minute or something like that. We're not going deep into this idea. And the point is when we compute the areas, the minutes disappears and we get pure numbers, which is what we want our probabilities to be. So that's our graph, okay? And we're going to use that graph to compute the probability we want to do next. So let's move to that now. What is the probability I wait more than 8 minutes? I'm going to write this question here with probability notation. This is the probability that our random variable W is greater than, and I guess strictly speaking, I didn't say or equal to 8, I said more than 8 minutes. And with random variable, continuous random variables, the difference between or equal and equal to and without is not consequential. But since I said more than 8 minutes, I will do it this way. So in terms of the graph, what this means is I'm asking for what's the probability that our wait time lives in this interval down here between 8 and 10. And what that will be is this area here. And it's really simple to see. That is a rectangle, right? The width is 10 minus 8, or 2. And the height, like the height of the whole thing, is 1/10. So that's 2/10, or 0.2 or 20% or 1/5. And I'm just pointing out all of these answers are equivalent and acceptable to me. So whatever you prefer, right? 1/5 is a nice reduced fraction. 2/10 is not. 2/10 is nice. 2/10 is nice because it lets us know where this came from a little bit. It kind of paints the picture. We had 10 up to 10 minutes available. Some of us like decimals. Some of us like percentages. I'm not one of those people. I wish percentages never existed, but people like them, so we have to use them. Anyways, those are all the same number, just different ways to write it down, and any of them are acceptable. So we have a 20% chance of having to wait more than 8 minutes, right? Or in other words, between 8 and 10 minutes, and we see that from the area there. Okay, let's complicate this one more time, just a little bit. Let's now consider the following situation. Let's say we've already waited 3 minutes. Okay, we're starting to get a little nervous. Okay, let's say if we know how long this bus takes to get there. If we have to wait 8 or more minutes, we're going to be late for work. So we're getting really nervous that we're going to have to wait that long and we're going to be a little late. So we are now asking, what's the probability? We've already waited 3 minutes. What is the probability we wait more than 8? Okay, so we're asking kind of the same question, that what's the probability we wait more than 8 minutes, but the situation has changed because we've already waited 3 minutes. Okay, so we're going to do this in 2 different ways. All right, well, first of all, let me write this question out in our probability notation. This is the probability that W is greater than 8, given given that W is already greater than 3, right? Because we've already waited 3 minutes. That's a given. That's happened. Okay. Well, let's just follow the rules, the definition of this conditional probability. There's a formula that tells us that the probability of A given B is the probability of A and B over the probability of B, right? That's the definition, one definition of conditional probability. And so in this case, this is like my A, this is like my B. So this is the probability that W is greater than 8 and W is greater than 3, divided by the probability that W is greater than 3. Okay. Now, keep in mind, let's reason through the numerator. The event is that we wait more than 8 minutes and we wait more than 3 minutes. Okay. We can boil that down to waiting more than 8 minutes. Right? Because another way to say this, let's just think about numbers. If I ask you, what are the numbers that are greater than 8 and they're greater than 3? They're all the numbers greater than 8. Because the numbers greater than 8 are greater than 3. The only ones we're missing, not the only ones we're missing a lot of numbers, but the numbers between 3 and 8 are greater than 3, but not greater than 8. So we can't count them because we need it to be greater than both. And the stuff less than 3 is less than both of them. So we can't count it. So that boils down to this and this. Okay. So let's sketch that picture again. I'll do it a little quicker this time since we've already seen it. Here's 10. Here's our horizontal line at 1/10. Let's use 2 different colors. Greater than 8, we already know, right? We did that one, so I might as well put that one in. That was, I'm going to write this as fractions unreduced right now, which we'll see why in just a second. Let's do greater than 3. 3 would be sitting here. And we'd be looking for this area. This area is going to be 10 minus 3 times 1/10, or 7/10. And that's going to be the area, that area represents the probability of being greater than 3. So we get 7/10 here. How do we divide fractions? We multiply by reciprocals. Our 10s cancel. This is why I kept it unreduced. And we get 2/7. So the probability that we wait more than 8 minutes, if we've already waited 3, is 2 out of 7. Okay? That's one way to approach this problem. Let's do one more thing. Let's do this in one more way. Okay. Once we've waited 3 minutes, we're in a new situation. We know now the bus will come in no more than 7 minutes. Right? We knew when we arrived, the bus couldn't take longer than 10 minutes to show up, but we waited 3 of them, so now it can take no longer than 7 minutes to arrive. Okay? What is the probability it takes more than, so now, remember, we already waited 3 minutes. We're asking about waiting 8 minutes. So now we're saying, what's the probability we wait 5 more minutes? Okay, since we already did 3 of the 8 minutes we were asking about. So I'm asking the same question, I'm just formulating it a little bit differently. 3 minutes have gone by, so now there's 7 minutes till I know the bus has to arrive. I want to know if I'm going to be late for work. I had 8 minutes when I arrived. There's 5 of those minutes left. So what's the probability it's going to take more than those 5 minutes? This is a new situation. I can give it a new random variable. I'm going to call it W star, right? It's kind of the same, but a little bit different because I've changed some of the details. So this is still a uniform random variable, and it goes up to 7 minutes because I'm starting now. I'm thinking from this moment. I already waited 3 minutes. Now I'm just thinking about from now until 7 minutes have passed. So W is, oh, I forgot to write that. Let's just put it here. W is the wait time in minutes till that bus arrives, starting right now after the 3 minutes have passed. Okay, and let's sketch ourselves a graph. It's going to look very familiar. 0 to 7. There's a nice-ish horizontal line. We know its height has to be 1/7. So now this question of what is the probability that we wait more than 5 minutes, is the probability that W star is greater than 5. Okay. The picture, here's 5. I want greater than 5. That's this area here. Well, we know the width of that rectangle is 7 minus 5, and we know the height is 1/7. So we end up with 2 times 1/7, or 2/7, which of course is exactly what we got up above, right? There was nothing wrong with either way that we just did this, so they better come up with the same answer. And they did, right? So the first one's nice. It follows our definition of conditional probability. It's a kind of, I don't know if algebraic is the right way to express the kind of work we were doing up there. This one illustrates another point about conditional probability. One notion of conditional probability is that it reduces our sample space. And if you look at our graph, it had gone from 0 to 10 in the original situation, but now it only goes from 0 to 7. So we've shrunk that sample space, right? And that's what conditional probabilities do. Once you know some extra information, some possibilities might have been eliminated. Some outcomes have been eliminated. So we have a smaller sample space, right? In this case, we've eliminated any of the outcomes of the bus arriving between 0 and 3 minutes. Okay, that is it for this one. Thanks, everybody. I will see you next time.